Let's demonstrate this formula in the context of a mixing problem. Assume you have a tank that holds 1,000 gallons and is 90% full. An additive is injected at a rate of 10 gallons per minute. The solution is mixed well and then drained out at a rate of 5 gallons per minute. The question is, what is the concentration of the additive at that moment when the tank is full? There are a couple of features to this problem we're going to have to analyze. First of all, we're talking about when the tank is full, so we've got to be concerned with volume. Also, we are told the rate of change of the volume, that coming in and that going out. Lastly, what we're asked about is the concentration of the additive in the tank. Let's set a few variables. First of all, V as a function of T is our volume. Next comes Q of T. That's the quantity of the additive that is put into the tank. So that when we talk about the concentration, C of T, that is simply Q of T over V of T. Let's derive the differential equation and then solve it. By considering flow rates coming in and out, it's easy to see that the volume is the initial volume, 900, plus 5t, meaning that the tank will be full at precisely t equals 20. If we consider the time rate of change of the amount of additive, Q, well, that additive comes in at a rate of 10 gallons per minute, but the fluid is drained out at a rate of 5 gallons per minute. That drained out fluid is not pure additive, but depends on the concentration, C. Thus, we derive a differential equation on Q as follows: dq dt plus Q over 180 plus T equals 10. This is a linear, non-autonomous ODE, where the function A is negative 1 over 180 plus T. That means our integrating factor is e to the integral of dt over 180 plus t. Of course, that integral is simply the log of 180 plus t, and when we exponentiate that, we obtain simply 180 plus t. If we therefore multiply the differential equation by this integrating factor, we obtain, very simply, 180 plus t times dq dt plus q equals 10 times quantity, 180 plus t. The left-hand side is the derivative of q times quantity, 180 plus t. Integrating both sides gives us on the left 180 plus t times q, on the right 1800t plus 5t squared plus a constant. You can show, based on the initial condition that there's no additive at the beginning, that integration constant is 0. Now we almost have the solution to our problem. What do we need to do? We solve for Q as 1800t plus 5t squared over 180 plus t. But we're asked about the concentration at the time when the tank is full. At t equals 20, we get the amount of additive to be 190. Therefore, the concentration at that time is 190 divided by the volume of the tank. That means that the additive is present at 19% when the tank is full. There are many similar types of problems for which integrating factors are helpful. Some of them are like this, involving mixing and tanks. Others come from entirely different applications. And indeed, this is just the beginning of the wonderful subject of differential equations, where there are many more families of differential equations that require specialized solutions. A few of these are doable with the tools that you now have in hand. But many of these differential equations require multivariable calculus. Some can be very difficult to solve indeed.
We now have in hand several types of ODEs, their solutions, and their applications. That's the good news. The bad news is most differential equations are hard to solve. Some seem impossible. In our next lesson, we'll consider what to do when the solution seems to slip from our grasp.